Kia ora and welcome to video 17 of the series Agile Algebra. This video here starts off quite nicely. We have a problem here involving rationalization, and the first quantity there that you're rationalizing is literally an achieved problem. The second one isn't that much harder, probably a merit question, and the third one is really hard unless you understand why rationalization works. So you need to multiply by conjugates. And usually it's obvious what the conjugate form is that you need. However, when there's a cube root involved, it's not so obvious. So have a go at the problem, and hopefully it goes well for you. If not, go through the solutions and see what I've done. You'll see that it is actually more tedious than you expect. From such a simple quantity, the answer blows up in your face. All the best. Okay, the thing I really like about this problem is that first part is just an achieved question. The second part is a really tedious achieved question. Probably you could argue it's merit. And the third one looks so similar, but it's way harder. And so it's really testing your ability to really understand what the achieved stuff is doing, rather than just go through the motions of the algebra, to explain So what I really like about this problem is that it really tests your understanding of the achieved concepts. So the leftmost expression is an achieved question. If you rationalize that and you go through the motions of the algebra, it's pretty straightforward. And the second one follows similar algebra. It's a little bit more tedious, maybe a merit question. And the third one looks so similar, but it's really tricky unless you really understand how the rationalizing process works. So let's have a look at the first one and kind of what's happening. We know from our achieved work that we multiply by the conjugate of the denominator. And I'd just like you to think about why that actually works. Okay, rationalizing the denominator means turn the denominator into a rational number. When we multiply by this conjugate, the numerator is root 2 minus root 3, which is irrational, it's got surds. The denominator, we have a difference of two squares there. So when we expand that, it's kind of like a quadratic a plus b, a minus b sort of thing. So we've got root 2 times root 2 is 2. Then they've got the cross terms, root 2, root 3, and minus root 2, root 3. They cancel, which is what we need in the rationalizing process. We need that surd to cancel. And then we have the last term, root 3 times minus root 3, which is minus 3. Okay, so the numerator is root 2 minus root 3. The denominator is equal to minus 1. So we may wish to write that as root 3 minus root 2. Switch it round by dividing by negative 1. So first one, achieved question. Pretty straightforward. And if we understand that the conjugate works because of the difference of two squares expansion, it's going to help us understand that third one, which is quite tricky. Okay, second one. 1 over root 2 plus root 3 plus root 5. So 3 surds. What we can do is we can group two of them together, and that will help us think about what we multiply the top and bottom by. So if I times it by root 2 plus root 3 minus root 5 on top and bottom. Okay, I've got to make sure I times the fraction by the same thing top and bottom, because if we don't, we're timesing by something other than 1. And when you times by 1, it doesn't change. If you times by something other than 1, you're changing the quantity completely. You can't do that. Okay, and if we are real careful with our expansion now, the top stuff, of course, is just 1 times the top right of the fraction, so nothing special there. Now the denominators, root 2 plus root 3 times itself. We've got a root 5 times the bracket. We've got a minus root 5 times the same bracket. So that stuff all cancels. I don't need to expand it. And then we've got root 5 times minus root 5, which is minus 5. And we haven't really finished because the denominator is still irrational. So if we expand that bracket out, we've got root 2 squared, root 3 squared, which is 2 plus 3 is 5, minus 5, the whole number cancels. And then we've also got two lots of root 2 times root 3. Okay, and to get rid of that surd at the bottom, we can times by a conjugate, or we can just multiply by, how about we just multiply by root 2 and root 3. Alrighty, so the denominator, there's still a 2 there. Root 2 times root 2 is 2. Root 3 times root 3 is 3. Now the numerator is 3 different terms, all multiplied by root 2, root 3. First term is going to be root 2, root 2, root 3, so 2 root 3. Second term is going to be root 3, root 2, root 3, so 3 root 2. And the last term is going to be minus root 5, root 2, root 3, which you could write as root 30 if you wanted to. And think, does 30 have any square factors? Nope, 4's not a factor, 9's not a factor, 16's not a factor, so that's all you can really do there. And we could then, if we wanted to, the whole thing is being divided by 12, so we could write 1/6 root 3 plus 1/4 root 2 minus 1/12 root 30 if you wanted to. Now the third part, this is where the real test of understanding happens. So what I'm going to do is start with a highlighter. I'm going to call this dude here equal to A, and I'm going to call this dude here equal to B. And right, because there's a cube root there, it's not going to be A minus B times A plus B. Like if I times by root 2 minus cube root of 3, and I try that expansion, the first third, root 2, okay, that's good. The cross terms cancel, but then the last term is going to be the cube root of 3 times the cube root of 3, which doesn't get rid of the third. So what we actually need is A cubed plus B cubed. A cubed plus B cubed, rather than A squared minus B squared or A squared plus B squared. So if I write down the factorization of that, how did I know this factorization apart from the fact I've also memorized it? For example, if I had x squared plus 8 equals 0, I know that one of the solutions to this problem here, x cubed plus 8 equals 0. I know one of the solutions to that problem is minus 2. So I know that x cubed plus 8 has a factor of x plus 2. And so all I've done there is generalize a cubed plus b cubed will always have a factor of a plus b, because a equals minus b is a solution. And then the rest comes from just expanding this out and going, that's a cubed, ba squared minus ba squared minus b squared a plus b squared a plus b cubed. So all the terms in the middle cancel except the a cubed and the b cubed. So that's how I've learnt that. Now, if I can use this special factorization to our advantage, given what I've called a and b, if I take this 1 over root 2 plus cube root of 3 thing, and I multiply it by root 2, remember a is root 2, so I'm going to multiply it by root 2 squared, which is 2. I'm going to multiply it by ab, which is root 2 times the cube root of 3, which seems so weird to do that. And then the b squared term at the end, b is cube root of 3, so it's the cube root of 3 squared, which is the cube root of 9. And if I times that top and bottom, Doesn't seem much simpler than what I started with, but it's going to make the denominator rational. Okay, and we're going to check this out long form rather than, oops, why am I putting brackets around 1? Just to convince you. So the numerator, 1 times that stuff. Nothing special. I'm using the dot for times if you haven't already worked that out. Cube root of 9 is not a nice number. Cube root of 3 isn't either. Now, this denominator, we've got 2 times root 2 plus 2 times the cube root of 3 minus 2. Okay, so I've done that dude and that dude. Now I'm going to do that dude, which is minus 2 times the cube root of 3. And this dude, which is cube root of 3 times the cube root of 3 is the cube root of 9. So we've got minus root 2 times the cube root of 9. And the last two terms, cube root of 3 times the cube root of 9 is the cube root of 27, which is 3. And, oopsies, I've missed a term, root 2 times cube root of 9 plus root 2 times cube root of 9. Does everything cancel? I hope it does. That term there cancels with that term cancels with that term, and we're left with 3 plus 2 root 2. I could have done this a different way if I had let, rather than a equal the cube root of 2, if I'd call that a cubed and b cubed, that would have been better, I think. Well, maybe not. Okay, let's see where I can go with this. Now I can, it turns into an achieved problem. So I need to then times by the conjugate of this. Actually, I think I am on the right track here. 3 minus 2 root 2, 3 minus 2 root 2. The reason why it didn't simplify in one step was because one of the denominators was a square root and the other one was a cube root. If they were both cube roots, then this would have fallen out nicely in one step. So now I've got this extra rationalisation to do, which is really tedious. Okay, the numerator, 2 times by both the things, 6 minus 4 root 2, and then minus root 2 times the cube root of 3 times 3 is minus 3 root 2 times cube root of 3, and we've also got minus 4 times the cube root of 3, and then the last two terms plus 3 cube root of 9 minus 2 times square root 2 times cube root of 9. Oh my goodness, the numerator is horrendous, but the denominator is rationalised because it's going to be 3 squared is 9. The middle terms will cancel, the surds will cancel, and we're left with 2 root 2 times 2 root 2 is 4 times 2 is 8, 9 minus 8. The denominator equals 1. So the answer to the problem is that. And okay, we've got a few things that we may be able to do with this. We could go, we could write 6 minus 4 root 2, and then we could factor out the cube root of 3 if we wanted to, and the minus. And we could also factor out the cube root of 9 if we wanted to. But that's really all we can do of it, because the cube root of 3 and cube root of 9 are not nice numbers, as I was saying. So, really tedious, but you wouldn't have got anywhere with conjugates unless you knew this sneaky relationship here between a cubed plus b cubed and that quadratic factor that we needed to multiply the top and bottom by. Hopefully you found that interesting. It's quite nice to take an achieved problem and really think about why it works and how to make it harder.